So far, we just used strong induction to prove things that we already knew how to prove, and we didn't really use the full power of strong induction for our coin problem, because we only needed to look at one place, k minus 3. So let's look at something that's a little bit more of a theorem, and also something that demonstrates usefulness of strong induction a little bit more. There is a theorem called fundamental theorem of arithmetic that says that every natural number greater than 1 can be uniquely written as a product of primes. So for example, if you have a number 12, you could write it as 2 times 2 times 3. 17, well, it's a prime itself, so it's a product of primes consisting of just one element, 17 itself. 30 is 2 times 3 times 5, and so on. And in order to show that every number can be written uniquely, we just need to assume one more thing, that we write primes in a specific order. So, for example, we don't really look at 2, 3, 2 as a way to represent 12. We just consider it equivalent to 2 to 3, and 2 to 3 is what we will consider as a proper way of writing, let's say, 12 as a product of primes. So there are two statements in this theorem. One of them is the existence statement that says that every natural number can be written as a product of primes. And this statement is the one that we are going to prove using strong induction. Another part of proving the theorem is to show that there is only one, no more than one way to write every number as a product of primes. And this one, let's skip for now. If you're interested, you could look at chapter 4.3, because we need some algorithms that you will see in 1001 in order to do a good job proving it. So let's just prove existence, that every natural number can be written as a product of primes. And by the way, here we don't really need to be concerned about order, because we're not concerned about different ways of writing a number. We just want to write it somehow as a product of primes. So here will be our proof by strong induction. So we'll start with a predicate that for a number n, there is a number m, which counts how many primes there will be in the product, and primes p1 to pm, such that n is a product of p1, p2, and so on to pm. The base case, since n is greater than 1, will be 2, and actually in this case we only need one base case. So if you're using strong induction, we could take a and b to be the same, to be 2. So 2 is prime, and if the number is prime, we only need to put that number in the product. So m will be 1, and our only prime will be the number 2 itself. For the induction hypothesis, let k be an arbitrary natural number greater than 2, and assume strong induction hypothesis that every number from 2 up to k minus 1 can be written as a product of primes. So for the induction step, we need to find a number, let's call it m prime, and the corresponding primes q1 and qm prime, such that the number k is a product of those primes. And as we often do, we will prove the induction step by cases. Either the number k is prime or it's not prime. And the case when k is prime is very easy. We don't really need induction hypothesis for it, because we know that if a number is prime, then m equals 1, and the only prime in the product is the number itself. So now let us do the harder case when k is not prime. So if k is not prime, then by definition of prime number, it means that it's product of some two numbers. Let's call them A and B. And here A and B are just two numbers that are somewhere between 2 and k minus 1. Well, both are less than k. Actually between 2 and square root of k. But the thing is that we don't know a priori what those numbers are. They can be pretty much anything, and we just know that they're not likely to be k minus 1. So here is where it's very useful that we are using the strong induction hypothesis, which just tells us they're between 2 and k minus 1, then both of them can be written as products of primes. And now we are pretty much done, because all we need to do is to write k as a product of primes forming A times primes forming B. So our m prime, the m corresponding to the number k, will be the sum of ma and mb. And if we want to remember the order, we can rearrange the primes in the list, primes from A and primes from B, from smallest to largest, and that will give us our q1 to qn prime. And that's it. That's the proof of the induction step and the proof of the existence part of the fundamental theorem of arithmetic. It says that every number which is greater than 1 can be written as a product of primes, every natural number. So it seems like strong induction is stronger. We just did a proof that really relied on the fact that we assumed our induction hypothesis that P of I would hold for every I between 2 and k minus 1. But in fact, induction, strong induction, and well-ordered in principle are all equivalent to each other. So when you are doing a proof, just choose whichever one seems most convenient. And you could actually prove that the three are equivalent, and the proofs are not that complicated. So for example, you could prove induction from well-ordered in principle, and we kind of went over it by saying that it's sort of the proof by contrapositive of the induction step and basis of induction. There is a smallest number where the predicate doesn't hold, either the basis of induction, or it means that, or we could show that from if P of k plus 1 doesn't hold, then P of k doesn't hold. We also can prove a strong induction statement by the usual induction, and for that we just make our predicate for all I less than n, P of n, and then we prove that new predicate by induction. And we could prove well-ordered in principle from strong induction, or actually even from normal induction, by showing by induction that 0 cannot be a smallest element, 1 cannot be a smallest element, and so on and so forth. Okay, so that pretty much completes our induction unit. We will talk more about a different kind of induction, but before we get there, we'll need to talk about a few more definitions. And to get into that, here is a puzzle about rabbits. And by the way, this puzzle is absolutely not biologically realistic, and it's a very, very abstract model of some kind of a process, just to get you thinking about what happens in processes like that. So here is a puzzle. A ship leaves a pair of rabbits on an island, and the island has a lot of food and no predators for the rabbits. It happened before, happened in real life. It was definitely more than one pair, but to simplify our proof, let's start with one pair. And after that pair of rabbits reaches 2 months of age, they produce another pair of rabbits. And after that, they keep produce a pair every month. The rabbits that were born after 2 months produce a pair of rabbits themselves, and like their parents, they keep producing a pair of rabbits every month thereafter. So here is the question. How many pairs of rabbits will be on the island in n months, assuming that no rabbits die? So at the beginning, there is just one pair of rabbits. At 2 months, it becomes 2 pairs of rabbits. At 3 months, it becomes 3 pairs of rabbits because the first pair produced another one. And then next time, both original pair and the first pair being born produce a pair of rabbits each, and then it goes from there. So how many pairs of rabbits will be on the island in n months?